Okay, so welcome to our first day of week 5 now. And let me tell you the plan of the day. As always, I'll start out with some questions and I can answer them, whether they're homework problems or whatever. And then after that, we have a really important definition. Again, every day is important. And today we do one definition, but pretty much there's a single thing we focus on and that's it. And that is what a linear transformation is. And they're important. We're going to see some of that today, but you're really not going to get the importance of it until we generalize. As I've mentioned throughout the class, is that for you all, vectors are a bunch of numbers with commas in between. They're kind of like points in R2 or something like that. But it turns out that vectors have a much, there's other ways of looking at vectors and defining them. And we're going to find out, for example, later in this class, that a derivative is a linear transformation and so is an integral. And you can do all calculus with linear algebra, but not today, because right now, the sign of x is not a vector today, but that's going to change. So I do want to let you know that this is really to prep you for where it's going to become really important later, but you want to do it in the easy way first, and then we're going to get more general and harder, is the idea. So I'll define a linear transformation, and then we'll look at matrices and linear transformations. And then we'll talk about the matrix of a linear transformation. So it turns out that there is really a solid coordination or a solid matching between matrices and linear transformation, it turns out. And as I've mentioned a bunch of times already, is that a matrix is a function. Today, we're going to see why. Today, we're going to see that it is a function, and it's a special kind of function called a linear transformation. Then we'll talk about, well, if you define a linear transformation in an inconvenient way, how do we come up with the matrix in a better way? And we'll see that it turns out matrix multiplication is what you're going to have to do. So today is kind of one of the days where we're actually going to see why we did the things we did before. So I will let you know that what we do today specifically is not on the exam. On exam 1, it is on exam 2, but we're going to use a lot of the old stuff, and of course all the old stuff is on exam 1. So still pay attention. Don't just say, well, I'm thinking about exam 1, so I'm just not going to bother. But you really should pay attention, because again, we'll be talking about some of the old stuff, and that'll help you review. And then we'll talk about exam 1. I have written exam 1, and I actually took exam 1 yesterday, and it's ready to go. And it's going to be Wednesday at this time, basically 1 o'clock. And that's when you'll do exam 1. I'll talk about what it's going to be like, somewhat at least, not every detail, but we're going to talk about how to prepare for it, what you should, what some of the main points are that you should make sure you know before you start taking exam 1. So that is the plan of the day. And again, the big announcement, which I'll announce again when I get to number 6, the exam 1 is on Wednesday. So 2 days from today, you'll come in. There's no Zoom session because you don't want me bothering you. So if you have questions, email me, whatever, and that's fine. But there's no Zoom session. I'm not going to give a lecture on Wednesday at all. So it's all going to be, you taking the exam and then submitting it is the way it's going to go. But take it seriously. Take it really seriously. So our next Zoom session after this will be on Friday, actually. And then we're back to normal again, starting Friday is the plan of the day. The plan of the quarter. So I see Ralph has a question about problem 16. So let me go and grab it. Okay. And open this. Oh, that was, sorry about that. I was reading the wrong one. Just a minute. 12, 13, 14, 15, 16. Here we go. Just a second. Uh-oh. Hello? Ooh, I got worried. My screen just died. That was scary. I got a black screen, but I'm back. Did anything happen to you guys?
No, but your video feed is frozen. Your audio's working just fine, but...
Oh, video's down. Okay. So sorry if you can't see me, but you don't need to see my face to be able to understand, hopefully, unless you're a lip reader and you can't hear, but sorry about that. It's still down? No video? Wonder, let me see if I can do something about that. Just a minute. Yeah, camera looks right. Let me stop the video and restart it. Sometimes that works. Turn it on, turn it off. Did that work?
No, it's just black now.
Still black video?
Yeah.
All right. You may not get video from me. Sorry about that. I'm not sure what else I could do than turn it off and turn it back on. Select a camera. That looks fine. Let me try virtual background. Sorry. Maybe I'll give a background. Maybe that'll matter. Yeah, it looks fun. There. I don't know if that helped. I think I do have to save it. Just a minute. That didn't work. Okay, we may not have my video, but again, you don't need to see me, but if my voice gets frozen, let me know in the chat box. So you can hear me though, right?
Yeah.
Yeah, I have no idea what happened. Literally my screen went black, completely 100% black. And then it came back on and I don't know. The little video light's on. It looks, I see my video.
Maybe your computer's GPU froze.
Maybe, but my video is showing on Zoom. Yes, I don't know. Oh well, I don't want to waste too much time, and that's like the least important. But it put antlers on me, so when it comes, if it does come on you, it'll be funny. Okay, so it says consider the following scalar equation of the plane: 2x minus 3y plus z equals 0. Find the orthogonal complement of the vector v equals 3, 4, 1. And notice that if you plug in 3, 4, 1, you get 6 minus 12 plus 1 is not 0. So it's not on the plane. If it's on the plane, there's all kinds of weird things going on. So there will be an orthogonal complement. Also find the point on the plane which was closest to 3, 4, 1. Okay. So do you understand what it's asking for first? Okay. So what we need to do is we need to figure out what this thing is. Well, it's a plane, right? So what I need, and notice it does go through the origin, right? And I've said more than once in this class that that a plane through the origin is a subspace. Do you all remember that? All right, so what it might help to do is to represent that subspace differently. As in, instead of as a plane that we're seeing, you know, in an equation like that, let's get a basis. So to get a basis, and I kind of did an example on Friday, but I don't know if you remember. What did we do to get a basis? Do you remember?
We plugged in some points and found some vectors.
Exactly. You find some, and I'm not a masochist or a sadist, so I'm going to try my points to be easy. Sound good? I don't want to put in fractions or anything like that. So how about, hopefully you'll agree that 1, 0, -2 is on it. Do you agree? Nothing magical there. zeros are good to have if you can get zeros, right? All right, so that let y be 0, right? So maybe I'll let z be 0 next. And let's not have fractions. So how about 3, comma, 2, comma, 0? Are you good with that? Again, nothing magical. I just said, hey, I want z to be 0. You know, I can do halves, but if I do 3 and 2, then I don't have to worry about fractions. Any questions so far? Okay. So next, we now have a basis. So how do we find the orthogonal complement of the point or the vector 3, 4, 1 to the subspace with basis 1, 0, -2, 3, 2, 0? And notice this really is a basis because these are not multiples of each other. And we know also a plane has dimension 2. Again, hopefully you know that from, I don't know when you learned that originally, but you know that planes are two-dimensional. So do you remember if you have a basis and you have a vector, how you get an orthogonal complement? Can you remember?
We had an equation for it.
Yeah, how'd that go?
It's going to be y be a point in Rn.
Mm. And
Dot
how do
it
we
with
find?
the W.
Right. So in this case, what am I going to dot? So our point is 3, 4, 1, by the way. And what am I going to do?
You're going to dot it with one of those vectors of our basis.
Okay, so let's do it just for fun. 3, 4, 1. Dot. How about 1, 0, -2? And what do you get?
It should be 0.
Hmm?
Should be 0, right?
No, it's not 0.
I got 1.
Yeah, it's definitely 1. So what did that do for us? So the idea is that something, we got a dot product. We do the other one too, just for fun. 3, 4, 1. And dotted with 3, 2, 0. Just for fun, since you want a dot. And what do you get?
17.
Yep, 17. Okay. But that's not the orthogonal complement. Those are just some numbers.
Now we need to divide each one by the magnitude of the second vector we dotted with of our basis.
Okay. So when you say each one, which is, what do you mean by each one?
So for our first dot product, we need to divide by the magnitude of the second vector.
Okay. So 1 over, I think I now need to do it in math mode. So 1 over, and what am I taking it?
Root 5.
The square root of 1 squared plus 0 squared plus 2 squared, which is root 5. So 1 over the square root of 5. Okay, and what do I do with that 1 over the square root of 5?
We're going to add it to 17 divided by the next magnitude of the second vector.
Okay, let me just go comma for now. And we're going to do 17 over the square root of, and what is that magnitude?
13.
13, good. Okay, and we had a formula. In fact, let me go find the formula so that y'all know what we're talking about. This is 4.11. Let me show you where it is. It's in there somewhere, but it always takes forever to go find things. These squares.
This almost looks like the Graham-Schmidt process.
It's kind of similar. So there's a point closest. So let me find it in a second. Let me do new share. There we go. Just want to get out of the book so you can see. Okay, so here's our orthogonal projection, right? So if W is a subspace of Rn and Y be a point in Rn, that's what we've got. We got the plane, which is a subspace, and then we have the point. And Z be a point in W closest to Y. Then we have these guys. A position vector Z is the Z equals the projection of W onto Y. Any questions on that? So basically we're finding this projection, and the projection, I think it already happened up a little higher. Here we go. So the complement, so the orthogonal complement is a set of all vectors that are orthogonal. And that's the definition. But the projection was really important. I think that was right here. Here's the orthogonal projection. So let W be the plane through the origin given by the equation. Find the point. This is a different example, but we'll see how this works. So what you do is you say, we take W1 equals U1, W2 equals U2 minus U2 dot W1 over W1 squared W1. Okay, that's to get the orthogonal basis. But then the complement, it's in there somewhere. I'm looking for it. Here we go. Find a basis for the orthogonal complement of W. So you get a basis, you can get a basis, which is right here. So in order for W perp, we want to make sure it's orthogonal. So that's why you take X dot U1 and then do the subtractions. Okay. Any questions on that? Okay. So they have, I'm just seeing if they have a formula, specific formula. They may not. I'm trying to remember where it was. But here's a point closest, basically what we just did. So we need to find the orthogonal complement. Okay, so let me reshare. New share. Okay, so what's next?
We need to square the magnitude on the bottom.
Okay, so when you square the magnitude,
We just get 5 and then 13.
yep, you get 5. Oh, I think I lost it. So we get 1/5 and we get 13. 1 over 13.
Yeah.
Okay, or 17 over 13, actually. Okay, and then what do we do?
Multiply that constant by our vectors, our basis vectors.
Mm-hmm. So what should I write?
Vector 1/5, 0, -2/5.
Mm-hmm. So So you're doing the multiplication all together, which is fine. So you get 1/5, comma 0, comma negative 2/5. And then how about the other one?
And then the other one will be 51/13. And then 34/50 or 13 and 0.
Yep. So kind of messy numbers, but not so horrible. And now what do we do with this? So what we did is we just multiplied them, right? And then to finish it off, what do we have to do?
Not quite sure.
Okay, we want to find the point on the plane closest to 3, 4, 1, right? You following that? Okay, so one of the things, if you want to find the orthogonal complement of the vector v, okay, that's not on this plane. That's just the orthogonal complement of this vector. Does that make sense? So it's kind of going with what you said, but we got to really think about this complement idea. We're going to use some of this other stuff in a bit to find the point on the plane closest, but that's you kind of did the second one before you did the first one, or you started working on it. So to do the orthogonal complement, what do we know? Well, for a vector to be orthogonal, that means that if you dot it, so let's suppose I have ABC. If I dot it with 3, 4, 1, what am I supposed to get?
0.
0. And let's do the dot product. You get 3a plus 4b plus c equals 0. Any questions on that? Okay, so basically we can say that c is equal to negative 3a minus 4b. Any questions on the very basic algebra? Okay, so if you want to find a basis for the orthogonal complement, then what we know is that the a and b are the free variables here, the way I've written it at least. Is that clear? Because that way I don't have to fractions. So if I let a be 1 and b be 0, I get 1, comma 0, comma negative 3. You following that? And if I get a be 0 and b be 1, I get 0, comma 1, comma negative 4. Any questions? Any questions on this? So then I guess I should put these in little curly braces and write span. Let's try again. So the span of the set 1, 0, negative 3, comma 0, 1, negative 4 will be the orthogonal complement of the vector 3, 4, 1. Anyone lost on that idea? And you can, how do you check your work real easily?
Dot both of them with 3, 4, 1.
Yep, and what do you get? When you do that dot product, what do you get?
0.
You get 0. Okay, which is good. That means they're orthogonal. Is that clear? So, and we know it's two-dimensional because we have in R3, we have a line or the vector space with one vector, which is a line, and a plane is orthogonal to a line. Right, and that one you should know from, I don't know, past experience, just visually. Any questions on finding the orthogonal complement? Okay, now if we want to find the point on the plane which is closest to 3, 4, 1, that's actually a different question because now we're finding a point in the plane, which is different than finding the orthogonal complement. So to find the point on the plane that's closest to it, what's another word for that? A single word.
Distance.
No, it starts with a P. That's a hint.
Pythagorean?
No, good try.
Projection.
Projection. Yeah. So we want the projection of this vector onto the plane. Any questions on that? So to find the projection onto the plane, well, we've already found a basis. So we did need to do that, right? And then once you find a basis, what you do is we can use the Graham-Schmidt to get an orthogonal basis. So I kind of let you go at it, and some of the stuff you did made some sense, but you didn't really need to do all of this. What we're going to do is we're going to do Graham-Schmidt. All right, GS for Graham-Schmidt. So for the Graham-Schmidt, our first vector is 3, 4, 1. Then our second vector is going to be 3, 2, 0 minus, and then if you remember, now I need to get math in it. We get a fraction. It's kind of what you were thinking. I didn't want to tell you too many things, but I let you go with it. But we need a fraction. And if you remember, you take the dot product of 3, 4, 1 and 3, 2, 0. And what I get is what 9 and 6 is 15, right? Okay, and then we divide that by the magnitude of 3, 4, 1, which is what, 26, does that sound right? So it's 9 plus 16 plus 1 squared. So square root of 26 squared. And then times 3, 4, 1. Any questions on that? Okay, and this is kind of messy. 15 should be 17, that's possible. Let me see if let's see. 3 and 3 is 9, 9 and 8. Yeah, it's 17. Sorry about that. Okay. And I'm not sure if I want to do the whole thing in my head and work out the arithmetic. It'll take a long time. I don't know if it's worth your time to watch me do it. But hopefully you all know how to do this arithmetic, right? With these awful fractions. Do you agree? All right, so what do I do? So now, and then the final step, once we've done that, is we divide by the magnitudes. So we divide each of these by their magnitudes, and that'll give you unit vectors. So once you have unit vectors, how do you get the projection? What do you do? So who remembers the formula for projection when you have an orthogonal basis? And now it has to do with some dot products. So what do we do? I don't see y'all jumping in. Who remembers? Hopefully I'm not, can you hear me? Nobody wants to talk, or maybe I can't hear you. I see everyone's on mute. Huh?
So from there, don't we do it again with another vector of our basis?
Yes, now we have the third vector,
Mm.
right? So now we have the third vector, but the third vector now is the vector that was given, right? Which was the 3, 4, 1. Let me make sure about that. Yeah. So we have this third vector, which is 3, 4, 1. And to get the projection of 3, 4, 1 onto the thing with this basis, which I just worked out. Where was it? Wait, 3, 4, 1. I'm a little worried about this. That was that guy. So our two vectors are 1. Oh, you know what? They're not. Sorry about that. They're 1, 0, -2. I knew there was a number weird. Sorry about that. 1, 0, -2 is what I want with the Gram-Schmidt. So I want an orthogonal basis instead of this basis that I've got here. This one's all pretty, but it's not orthonormal. So it's actually 1, 0, -2, and then this should be 1, 0, -2. That should be 3, 2, 0 minus, and then I should dot these guys, and I should get 3, just 3 when I dot them. Over, let's see. One times 3 is 3, that's right. And then this guy is over 5, not 26. Sorry about that. And 1, 0, -2. I was getting the wrong vector. That's a nicer, it's not great, but it's better. So if this one I can actually work out in my head. Otherwise it wasn't going to be nice. So 3 minus 3/5 is what? 15 minus 3 is 12/5. Comma 2, comma 6/5. Okay, so I now have two vectors, and then I take the norms and divide them, or the magnitudes and divide them. And then how do I get the projection once I know that? I take my 3, 4, 1, and what do I do with it? Who remembers? So I take the 3, 4, 1, and I subtract. Do you remember? Right. So if I want to find the projection, I take these guys and I subtract. Okay. So let me remind you the formula again. It looks like none of you are kind of coming in with the answer. So let me get you the formula. And it's here. So here's the formula, and that is the projection of W onto Y is Y dot W over W1 squared times W1 plus Y dot W2 over W2 squared times W2. And that's what I want. So I'm going to dot my vector with each of the vectors, divide by their magnitudes. Now, if I have an orthonormal basis, the magnitude is just 1. So I don't have to worry about the denominator. Okay, if I don't have an orthonormal basis, which is fine, then I have to divide by the magnitudes. So I go ahead and do that. And what do I get? So I need to take a dot product of y, which is 3, 4, 1, with 1, 0, 2. And what's 3, 4, 1 dotted with 1, 0, negative 2?
It's all that stuff we did up top.
Yeah. Yeah.
Mhm.
So we actually needed that. Okay, and that was 1. It's kind of nice. And then we do what was on top, which is divide by the magnitude of the 1, 0, negative 2, which was 5. And then we're supposed to multiply it by 1, 0, negative 2. And then we're going to go plus. And then we take this mess and dot it with 3, 4, 1. And that's just awful, right? Do y'all agree? But I'm going to say 3, 4, 1 dotted with 12 fifths, comma 2, comma 6 over 5 over the magnitude of 12 fifths, comma 2, comma 6 over 5. And where am I? And then times this vector. I think I'll just copy and paste it. And that'll give you your projection. Any questions on that? It's messy. Any questions? Sorry if it took a little longer than it wanted, but this is kind of a messier one. I think I should talk about linear transformations, which is not going to be nearly as messy. That's the good news. We're done with messy. Okay, so this is a big definition. It's the only definition today. It's the only main definition today. We're going to do stuff with it, sub definitions and stuff. But linear transformation is one of the biggies. So just let you know, kind of important definitions in this class. Kind of the top 5 maybe or so is span. And then what come after span?
Bases.
Yeah, basis.
Basis came after something, there's something in between.
Linear independence.
Linear independence. So span, linear independence, basis, dimension is important. Hopefully y'all remember dimension. And I'm saying these because this is a review for the test. And then the next biggie is linear transformation. Okay, those are the biggies. Okay, we're gonna have a lot more definitions, but those are the biggies. So I just want to let you know this is a big definition and it's not that hard. So let T be a function from Rn to Rm. Okay, I want to let you know that we are going to replace this definition. Instead of Rn and Rm, we're going to say V to W, but not today. But I wanted to get you ready for that. That it doesn't necessarily have to be Rn and Rm. It could be any vector space, it turns out. But since they're kind of easing you into it, they're letting it be going from Rn to Rm, such that for every vector V in Rm, T of V is in Rn. So in other words, it actually works. It is a function. Otherwise, it's not a function, right? Then T is a linear transformation if. And the book does it in one shot. I like to do it in 2 because it's easier. A little more writing, but it's easier to understand and show. And that is T of V1 plus V2 equals T of V, T of V plus W equals T of V plus T of W. Have you seen something that looked kind of similar to that before?
Yeah, it looks like function composition.
Well, there's that, but something that we've done in this class.
Matrix multiplication.
Yeah, but something more recent.
Is for close under addition.
Yeah, so closed under addition. Do you remember that? When we did subspaces. So that's why I put it this way, because I wanted to give you the reminder of subspaces. Okay. And then the second is T of KV equals KT of V. Doesn't that look like the subspace definition? I don't have the third with 0 because there's no 0 issue with linear transformations. So these are the two biggies. So I want to give you a heads up of what's going to happen next month, or maybe late this month. We're already February. And that is that we're going to be more general. And where have you seen these properties in calculus? I know it's been a year, or actually just one quarter. You had calculus last quarter.
For parametric equations.
Parametric. I don't know.
I was thinking integrals.
Yeah, integrals. Remember you had this with integrals, whether it was a triple integral, a double integral, a single integral. You always had that property. Do you remember that? And where else have you seen it? Before integrals.
Differentiation.
Yeah, derivatives. Okay. And as I mentioned, that's how we're really going to use it, but we're not ready yet. But I want to give you a heads up that that's really one of the main purposes of this is for that, but we're not ready to do it yet. But there's a big definition. Any questions on the definition? Okay, so just a note. I wonder if I can do that. There we go. So this is equivalent, this is the way the book does it basically, to T of AV plus BW is ATV plus BTW. Okay, and that's because if you let A and B both be 1, do you see you get number 1? And if you let A be K and B be 0, you get number 2. But I really think it's easier. I really think it's easier to do this as as 2 properties than 1. Okay, a lot less messy typically. Any questions on this definition? Okay, so let me ask you. All right, let's suppose let T go from R2 to R2. Where is that arrow? There it is. Such that T, actually, I think I need to keep it in the equation. T of AB, how about XY, is equal to X plus Y, comma, X squared plus Y squared. Is T a LT? LT means linear transformation in this class. What do we have to do?
Use our properties to make it look a little different.
Yeah, but here's what I recommend. Same thing with subspaces. It's the same first step, and that is guess. Look at it. Does this look linear?
No.
No.
Right. It just feels wrong, doesn't it? Okay. The first part doesn't look too bad, right? But that x squared plus y squared, it just doesn't feel right for linear transformation, right? Which means if we think it's not a linear transformation, all you need is one example that makes it not work. Any questions on that? So you just need one example that makes it not work. So I'm just going to do one and see what happens. Okay, so what we want to do is we want to see, does this work? So let's suppose that V equals, I don't know, how about 2, 3? And let's say K is equal to 5. Sound good? See what happens. Usually when something's not a linear transformation, it just fails in like anything you choose as long as it's somewhat random. Okay, not always true, but it's a good try. Just try to put some numbers in and see what happens. Well, let's look at what T of KV is. So 5 times 2, 3. Well, that's equal to T of 10, 15. Any questions on that? And that's equal to 25. Do you see how I got 25? Any questions on that? And then x squared plus y squared is 325. 10 squared is 100, 15 squared is 225, 100 plus 225 is 325. Any questions so far? Now what do I have to do?
Check your other property,
Yeah, or check not the other property,
but check to see if it's valid.
the other side of the equation. So now I got to see, what about K times T of V? So about 5 times T of 2, 3. And see if I get 25, 325. Any questions on that? Well, that's equal to 5 times, well, T of 2, 3 is going to be 5, comma, because 2 plus 3 is 5. And then 2 squared plus 3 squared is 4 plus 9 is 13. I can multiply the 5 through and I get 25. So the first one worked, right? But the second one is 65. And that's not equal to 25 to 325. So what's the conclusion?
This is
Not a linear transformation.
Yeah.
Yep. T is not a linear transformation. So to show something isn't a linear transformation, one example is all you need. To show it is, one example is never enough. Got it? Any questions on how I just did this example? Okay. How about, let's do a different one. How about T from, let's do this. How about R3 to R2, just for fun, with T of XYZ, because I need an R3 now, equal Z, comma, X minus Y, comma, X. Is that a linear transformation? With this new T. So what do you think? Does it look linear or does it not look linear?
Looks linear.
This one looks linear, okay? So this one we think probably is, which means should we just grab an example and hope it works? What do you think?
Yeah, why not?
Should we grab an example?
Sure.
No. If you think it's linear, don't do it. Don't grab an example. Totally wasting your time. So if you think it's linear, we need to actually write down the two rules in general and prove that they both work. Does that make sense? So let's look at, instead of an example, we're going to look at the question. Actually, I forgot to put the pointies. There we go. So what is T of, I'm going to go ABC plus DEF. I know I mentioned calculus, but we can get away with it. We're not doing calculus yet, so I can use D. Well, that's equal to T of A plus D, comma B plus C, comma C plus F. Any questions so far? Now, by definition, what is that equal to? What's the first component?
TA plus D.
TA plus
no.
TD. TA plus TD.
No, T's gone. That's a hint.
A plus D, comma B plus C, comma C plus F then?
No, that would be if T was the identity. T is not the identity. T is Z, comma X minus Y, comma X.
Oh, Z times A plus D plus am I on the right track here or?
There's no times. That's a hint. Okay. This says take the third component and put it in the first component. Do you see that? So T of A plus D, B plus C, C plus F, the first component will be C plus F because that's our Z. Anyone lost on what I just did there? Okay, then it says X minus Y, and that's A plus D minus B plus E. And I'm going to multiply the minus through. Minus B minus E, comma, then it says X, and that's A plus T. Any questions on that? You had trouble coming up with that. Does it totally make sense now, or did I lose you somewhere?
Nah, it makes sense now.
Yeah, it's following the rule. And the rule for T is that the first component of T of X, Y, Z is the Z, the third component. The second component, subtract the first two components, and that's the second component, the new one. And the third component is the old first component. So now I take T of A comma B comma C plus T of D comma E comma F. And I'm hoping to get what I got on the line above. So let's do it. That's equal to, well, I need to grab the Z or a C in this case. And then X minus Y is A minus B. And then X was A. And then plus T of DEF, the first new component will be F, because that's our Z. And then X minus Y is D minus E. And then X is D. And then I add the two vectors. And I get C plus F, comma, A minus B, plus D minus E, comma, A plus D. Are they the same?
Yes.
Yeah. The second component looks a little different, but they're not any different, right? All right. That's number one. Now what do I have to do?
Do the same with K.
Yeah, so T of K, ABC, is equal to T of KA, KB, KC. Which is equal to KC, comma, KA minus KB, comma, KA. Anyone lost on that? And then I have to take K of T of ABC. And that's K times C, comma, A minus B, comma, A. And if I multiply the K through, I get KC, comma, K, A minus B, comma, KA. Are they the same?
Yes.
Yes.
So therefore, T is a linear transformation. Any questions on this? Kind of busy work, isn't it? A lot of writing, not hard math, but you have to know what to do. But just a lot of letters, a whole lot of letters. And that's something about this class. There's a lot of letters in this class. Okay. So here's a big theorem and an important one. And that is, if you let T of V, vector V, equals A times V, where A is a matrix, then that's always a linear transformation. Why is that true? How do you show it's true?
By doing what we just did.
Yeah, now it's not going to be A plus B, A, B, C anymore because we don't even know what Rn is. Let's call it V plus W. Well, that's equal to A times V plus W. But T of V plus T of W is equal to AV plus AW. Any questions on that? Are they equal?
Yeah.
Yeah, because the associative, the distributive property works for matrices. And then the second one is T of KV equals A, K equals A times KV. And T, KT of V is equal to K times AV. Are those equal?
Yes.
Yeah, that was a property of matrices. You can pull constants out. Do you remember that? It happened. Okay, so that's the proof. I like simple proofs and I'll do them. If it takes too long, I won't, but that's a quick, easy one. Okay, so this is a big deal. Now comes the bigger deal, or one that may be a little more surprising, and that is you can go in reverse. So let's suppose that T is a linear transformation. Then there exists a matrix A such that TV equals AV. So what this says is that all linear transformations are just matrix multiplication. Any questions on that? Okay, let me mention something. And this is going to come up later, but it's so important. I figured I should say it now so I can say it again later. And that is What was the kind of the big two examples of linear transformations that we're going to do later that we're not ready for?
Integrals and differentiation.
Yep. So what this says, once we get there, we're not quite there yet, and it's not happening today. A derivative is matrix multiplication. And an integral is matrix multiplication, period. Is that weird thinking?
That is weird. I can't even picture it.
Yeah, we're not there yet. We're not there yet. But it really is. There's a matrix that is the integral matrix, and there's a matrix that's the derivative matrix. And we'll get there. There are some issues, of course, so don't think that you didn't need any calculus because, you just do matrix multiplication, which is so much easier, isn't it? You don't have to remember any of the techniques of integration. You just multiply by a matrix. But there's a little more said than that. But I will let you know that this is a big theorem that's going to be used in a big way later. So whenever you have a linear transformation, you can write it as matrix multiplication. And that's what this big theorem says. And this proof, because a lot of subscripts, and it's such an important theorem, I wanted to have the proof here. And here it is. So if A is a matrix with columns T of EI, okay? So let that be the matrix. Then we know that V can always be written as x1 E1 plus x2 E2 all the way up to xn En. Do y'all agree with that? Maybe I'll give you an example because it's kind of messy to look at, and then you see an example and you can say, of course. So let's do an example of doing what I'm doing in this proof. So let's suppose we have 3, 5, 1. Well, I can rewrite that as 3 times 1, 0, 0 plus 5 times 0, 1, 0 plus 1 times 0, 0, 1. Are y'all good with that example? Any questions on that? Do you all agree that was easy? And basically you could do this with any vector in any dimension. You can always break it up. That's what this says. As the coordinates times each of the standard basis vectors. So I can write AV is equal to A x1 E1 plus ... plus xn En. Okay, but then I can use properties of matrices, and I can write that as x1 AE1 plus ... xn AEN. Because remember, the x's are constants. So I could pull the constants out. But AE1 is T of E1 by definition. AEN is T of EN, and all the middles kind of work that way too. But now I have a linear transformation, and when you have a linear transformation, you can put the x's in, and you can bring in the pluses and write it this way. T of x1 E1 plus ... plus xn En. But x1 E1 plus ... xn En is just V, and that's the proof. Any questions at all on the proof?
So T is a number, or is just a vector, or is just a representation that we use?
Now, did you say T?
Yeah.
T is a linear transformation. It's a function.
Okay.
Right? So it's a function from Rn to Rm. And it turns out that if you have a function that's a linear transformation, you can always write it as matrix multiplication. Does that make sense? That's what this theorem says. So here's an example. Okay, let's suppose that T of 2, 1 is 3, 0, 2, and T of 1, 1 is -1, 1, 0. Let's see if we can find the matrix for T. Any questions on the example? Okay, and we're given this linear transformation, and we want to find the matrix. How might we do that? Any thoughts?
Well, it looks like we have vectors, so we could start there.
We have vectors, definitely.
So maybe we could set them up as either columns or rows to start.
We're not quite there yet. We'll get there. We'll get there. There'll be columns and rows, but we're not quite there yet. You might, I mean, unless you like can do all steps in your head, but I'm not going to. What I can write is I want to find out what T of X comma Y is. Are you good with that?
Yeah.
And I want to write it as a matrix. I want to write it as A times XY. In fact, I need to do it this way. Takes a while to write it correctly. That's what I want. Do you agree?
Yeah.
Okay. So what I do is I think about this proof is I want to write it correctly. So if I can figure out how to write XY in terms of 2, 1, and 1, 1, I'm in good shape. So I'm going to write XY is equal to A times 2, 1 plus B times 1, 1. Any questions on this idea? And I want to find A and B in terms of X and Y. Is that clear? Okay. And in fact, I really don't even need all X and Y. I can do 1, 0 to start with, because in the proof, I just need to see what happens to E1 and E2. So let's see what happens to 1, 0. Well, I can turn this into 2 equations, 2 unknowns. And what I get is 2A plus B is equal to 1. Maybe I should write in the next line, though, because that's the first component. And the second component is that A plus B needs to be equal to what?
0.
Equal to 0. And now I get a matrix. So our matrix equation oh, not there. It's next one. That one. So this matrix is 2, 1. In fact, maybe I'll do it augmented. There's different ways of doing it. Let's see. I think I'll do 2, 1. 1, 1. Times AB is equal to 1, 0. Any questions on how I turn this system into a matrix equation? All right, well, how do you solve that?
find the inverse of
Exactly.
2, 1, 1, 1.
Right. So I'm going to find the inverse. And now I can say, let's do this. That AB is this matrix inverse times 1, 0. Any questions on that? Which is equal to, now remember the inverse, the determinant is what? 2 times 1 minus 1 times 1, which is 1. Do you agree?
Yes.
The adjoint is, if you remember, you switch the 2 and the 1. That becomes a 1. This guy becomes a 2. And then you make the others negative. Remember doing that? And then times 1, 0. Any questions on that? Okay, and I can solve that. So what do you get?
1, -1.
We get 1 and -1. Yep. Any questions on that? All right, what's next? Okay, I just found it for 1, 0. Now what do I have to find it for?
Is it K0 or?
No, I'm not proving it's a linear transformation.
Oh, okay.
I found
0,
it.
1.
Yeah, then I do it for 0, 1. And if you look at what I did, the only places 1, 0 happened is here and here and here. Do you see that? So I can literally copy and paste this whole thing. I probably don't want to call it A and B anymore. I'm going to call it C and D now, because they're different. And make that 1, 0, 0, 1. Ah. Because I've done all the work. And what do I get?
-1, 2.
Mm-hmm. Any questions on that? Let me show you what I really just did. What I really just did is the following. See if I can just do what I want. There we go. Ah, wrong one. Oh, that's fine. So I multiply by 1, 0, 0, 1. Do you notice that? That's what I really did, is I multiplied that inverse by just the identity. So guess what? It's just the inverse. Are you following that? So once I find the inverse, I've really found my coefficients. And that's it. So what we can say is that A is really just this inverse matrix, which is this guy. So A is 1, -1, -1, 2. Anyone lost on that? Weird stuff? Okay, will this always work?
Only if T is a linear transformation.
Right, so yeah, if it's not a linear transformation, you're not going to find a matrix. Okay, but if you're looking for the matrix and you're given where it sends something else, you can just find the inverse of that matrix and that works. Does that make sense? And that's your A. Any questions at all on this linear transformation idea? Any questions? Okay,
So-
one good, yeah, question?
I do. So when you were going through setting up your system, why did you choose 1, 0 and then 0, 1? Was it because it doesn't change anything?
Yeah, I basically went to the proof. See the proof?
Yeah.
See E1? E1 is 1, 0. And then after this plus is a X2, E2, and that's 0, 1.
Okay.
So basically, I just took the standard basis. And that's how you do it. Any questions on that? Okay. And now what did I just find? What haven't I used yet?
X's and Y's.
No, I haven't used the 3, 0, 2 and the negative 1, 1, 0 in the example, because that's what we're trying to find, right? What I did is I figured out how to write this vector in terms of, so I guess I shouldn't write this A. I'm going to call this B, the better letter, because I didn't find the A yet. I found B. See, A is not going to be a 2 by 2 matrix. It can't be a 2 by 2 matrix because we need to end up with a 3 vector. Do you see that? Any questions on that? But what we know now is that we know how to take a vector and turn it into something in this weird basis, 2, 1, 1, 1. Any questions on that? But once we know how to do that, then we can put in our T. So what we're going to do is we're going to take this B and we're going to multiply it by our 302 negative 1, 1, 0. Any questions on that idea? So I'm not done yet, but I'm done with the first step. So now what I'm going to do is I'm going to realize I have this matrix kind of with this weird basis, 302 negative 1, 1, 0. So had this been the standard basis, and I just write that matrix. Do you see that? But instead, I need to do the B first. So I need to take my X, Y, I need to turn it into the A, B, C, D. And I do that with this B matrix. So then finally, I can write down what A is. And let's do this. So here's what A is. A is equal to, I'm going to first do this matrix to turn it into this weird basis. Then I'm going to apply T using its matrix. And its matrix is 302, negative 1, 1, 0. So let's write that out. 302, -1, 1, 0. Any questions on that? All right. And hopefully you know how to multiply matrices. So first thing is you take 3, -1 dotted with 1, -1. And what do you get?
4.
4. Then you take 3, -1 dotted with -1, 2. And you get -5, right? Okay, then we take 0, 1 dot with 1, -1. You get -1. Then we take 0, 1 dot it with -1, 2. You get 2. And then we take with 2, 0 dotted with -1, 1, -1, and you get 2. And then we take 2, 0 dotted with -1, 2, and you get
-2.
-2. Yep. And there's our matrix A. So remember that these are functions and you read it backwards actually. So first you do the 2 by 2 matrix and then you do the 3 by 2 matrix because functions are read in reverse. You remember that? F of g of x means do g first, then do f. So same thing with matrix multiplication is we're going to do this first, this 2 by 2, and the 2 by 2 is what takes something in the standard basis, turns it into this inconvenient basis, and then I can apply the transformation on the inconvenient basis, and I get this matrix. Any questions on that idea? I'll let you know we're going to have another section where we do this again, but more sophisticated and more stuff going on. Just let you know that.
I wish I could see this being done on a whiteboard, honestly.
I wish I could too, but you know, it is what I can do.
Yeah.
Yeah.
It just sometimes it gets confusing, like seeing the Word document. I don't know.
Yeah, sorry.
And
maybe
then I get into the homework and it feels more intuitive. Yeah, maybe in March, hopefully.
Maybe in March I'll be able to convince my dean to let me come at least for a review for the final. But I figure they're not going to let me in now, but maybe in March they'll let me in, late March. Because as I mentioned, I've been vaccinated and you guys are just from looking at you're pretty young, so you're probably pretty safe. Just got to stay away from your grandparents. But they've been vaccinated if by then. Any questions on this idea? Okay, I want to spend the last 10 or 11 minutes, or I guess I got 20 minutes to talk about what's coming Wednesday. Y'all better remember.
The exam.
Good. If you don't remember, then I don't know where you've been. So the exam is on Wednesday, and I want to kind of make a point is that the exam is at the same time that class would normally be. So it's going to start at 1, it's going to end at 2:45. Any questions on that? And here's what I'm going to do is that at 1 o'clock, I am going to put your exam in the Canvas exam button. And then you'll be able to see the exam. Okay, right now you can't, I don't think you even get to the exam, but it'll open up at 1 o'clock. So at 1 o'clock, you're going to go to Canvas, you're going to hit start the exam. Does that make sense? And right now, I don't know what it does. Maybe I'll look to see if I were a student. I haven't put it in yet, so I can safely show you. Just a minute. Okay, so here's your syllabus. And let me go. That's kind of a pain. I have to go and be a student. Otherwise, I won't be able to see it. Let's go to, sorry, you won't be doing this, but it takes a bit for me to show you what you'll be looking at. All right, so right now, if you go to the syllabus, let's see what it does. I haven't actually checked to see what you guys are looking at. I've only seen what I've done. Then it shows exam 1, right? And if you click it, all it says is submit assignment, no content. Is that clear? So right now, if you went and looked at the exam, you won't see anything. But at 1 o'clock, if all goes well, at 1 o'clock on Wednesday, your exam will be sitting there. Any questions on that? I'll put the content in. So you do not need to write out the exam questions, but you should write down the question number you're working on. Does that sound fair? So you write down number 1, and then you start working it out on a piece of paper. And then you write down number 2. And then once you're done, you're going to take a picture of your exam, just like you do for the homework. You're going to hit submit assignment. Oops, sorry about that. What just happened? One more try. You don't hit a assignment. You got to upload first. And there should be an upload button somewhere.
You just have to press submit, and then the upload option will pop up.
Okay, I think what's happening, either Zoom is in the way and I can't see it. That's possible. Or because I'm not the student, it's not giving me anything. It's hard for me to see what you guys are going to be looking at, but it should show that. And then you're going to upload and it'll happen. Okay, just like your homework. And then you're going to upload just like you're used to doing in the homework, and then it should work. Any questions on that idea? So this is a regular paper and pencil exam. The only difference is that you're at home. Okay, and you're on your honor to not cheat. And I will let you know that it's really not worth cheating, because as I mentioned, and I only mentioned it this year, I've never mentioned it before. So don't tell next year's student about this, and that universities don't look at your grades. Do you know that?
That's what I've heard.
Yeah, because if you've already applied, because they're not going to know, your application's in already. Does that make sense? So you don't have to, you need to pass, but more importantly, you need to learn this stuff. And if you don't study for the exams, you're not going to learn anything. I mean, that's really part of it, so that you can do well when you get into your engineering class or your graduate level or your upper division physics classes. Because if you don't learn this stuff, you won't be able to do the upper division stuff. This is an important class. So there's no reason to cheat, is what I'm trying to tell you. Sound fair?
Yeah.
But I do have you have to sign here to say that you didn't cheat. I think that's question 1, if I remember right. Any questions at all on what it's going to kind of look like for you? This is totally new. Do you think this is legit? Like, I mean, do you think you're happy with this? So I'm making this up as I go along.
I mean, I don't know what else we would do.
Yeah, I'm not sure what Bruce did. Did he do something like this?
Yeah.
Okay.
Yeah, vaguely.
Yeah, because like I said, I don't know. I don't actually talk to Bruce about how we teach. I use Proctorio for the classes where the grade matters, but this one doesn't. So I figure there's no reason. And Proctorio is kind of a pain. I think you all agree with that, right? Do you agree?
Yeah, absolutely.
I'm not doing it to me. I don't do Proctorio to be mean to students. I do it to stop cheating. So that's just a note. So what does the exam cover? So let's leave student view. So it should be pretty clear. You've been students long enough. You've had me more than once. And the exam covers everything we've already done up that's homework up to today's homework, the homework that was due today. So you're going to have to understand how to get a matrix out of a system, possibly. You're going to have to know how to do arithmetic of matrices. You're going to have to be able to get determinants, understand determinants and their properties. You're going to have to understand span, linear independence, basis, all that kind of stuff that we've done. You're going to have to know orthogonality and Gram-Schmidt. And I want to ask you something. Would you rather have it be a shorter test or a little bit longer?
Does longer come with the trade-off of more easy questions, quote unquote?
Not easier, but so if there's
less time consuming, I guess.
No, that doesn't matter. But if there's 8 questions instead of 9, then if you get one wrong, you only lose 12.5%. I'm sorry, you lose 12.5%. Whereas if you get one wrong, if there's 9, you lose only 11%. Do you see what I mean?
Yeah.
So like if I only gave you one question, it's all or nothing. You either get 100% or a 0%. And that sucks, doesn't it? Because if you didn't know that question, then you're screwed.
That would be a bummer.
Yeah. So I have to decide what's a good number of them to do. So I'm thinking about getting rid of one question, but it would mean that there's going to be one topic I can't cover. That you're not going to see, one more topic. Because there's been a lot of little topics. Would you rather have a somewhat shorter test? No, it's still partial credit. And in fact, if you don't show the work, there's paper and pencil, so you should show your work. Okay, that you don't have to say, well, it took too long to type. There's none of that. You're doing that on paper and pencil. So you do need to show your work. But I will go over, let me unshare my desktop just so I don't make a mistake. This way I'll know for sure. And I want to see something. Let's see if I can, one more try on the video. Did anything happen on video-wise?
No.
Let me try this. I don't know. There's only one camera. Sorry.
Is your webcam wired or is it built in?
It's built in, and it's actually lit up. It's showing it's working. I'm actually seeing me.
Huh.
That's why it's weird. I'm seeing me on my screen. So I don't know what's up. I've never had this happen before.
Yeah, I have no explanation at all, really.
Yeah, because usually I don't see me if it's not working. Did that do anything?
Yeah, the only thing I can think of maybe fixing it is like, rebooting Zoom, but
Yeah, but I don't want to do that because then we
exactly
go back in. All right. Well, hopefully it'll work next time I try. Sorry about that. I didn't do it on purpose. Try again.
There it is.
Really? Do you see
Yeah, it's working now.
I did that for fun. So I don't know what happened. I tried it on and off and it didn't work 3 times. The 4th time it worked. Okay, so just a note. I did this so that I can comfortably look at the test and not worry that you're seeing it. That's why I'm not sharing the screen. Does that sound fair?
Yeah.
Because I don't want you to see the exam. Just a minute. Let me open it. All right. So I will tell you question number 1. There's an A and a B. And I'm going to tell you the first 5 words. Oh, it might be 4 or 5 because I put a the in one, not the other. And it says, without the use of technology. Okay? So that's serious, by the way. How am I going to know?
You haven't told us because you don't want us to know how you're going to know so that we could.
No, I'll tell you how I'm going to know.
Oh, okay.
I did it with technology using more than one system. And it showed the steps, like Symbolab or whatever. And boy, did they make it horrible and messy. So, and specifically, I'm telling you that you're going to have to do it in a certain way and the computer won't do it that way. Does that make sense?
Yeah.
So if you don't follow the instructions, that means you used a technology. So I will know if you use technology because technology does it in an awful way, whereas humans don't. And I particularly grabbed 2 examples where that happened. So don't get tempted. Got it? Okay. I will also tell you that I actually did these problems, and the numbers are beautiful and nice. Got it? But I will tell you, if you use technology, the numbers will be messy and horrible. And I'll know. Got it? Okay. And I give you some instructions that you have to do it the way I'm instructing, which a computer won't do. Sound good? Now, what I'm going to ask you, what kinds of things do you think I could ask you to do by hand?
Find
Maybe
the inverse.
RREFing.
Okay,
Yeah.
REF is definitely a possibility. What else?
Matrix multiplication.
I could ask you to multiply 2 matrices. What else?
Find an inverse.
Okay, I could ask you to find an inverse. And by the way, I could tell you how to find the inverse, because remember we had a few techniques. And you have to, if I give you instructions, you have to follow instructions. What else?
Find the span of a set of vectors.
No, I'll let you use technology on that.
The Gram-Schmidt process.
Yeah, Gram-Schmidt could happen.
Determinants.
Yeah, determinants, definitely no by hand. Okay. Projections, no, I'd let you use technology for that, because the numbers are so messy with projections, aren't they?
Yeah.
So again, I promise you the numbers are not horribly messy.
Rank.
Okay, rank. Okay, and you better know, if you know how to RREF, you better be able to find rank. Got it?
Dimension.
Yep, dimension. Okay. And so you should know how to do all those, but I will let you know only question 1, A and B, ask you to do by hand. If you do all of the rest by hand, you know what's going to happen?
It'll take like 4 hours.
Yeah, and you won't be able to submit it. You won't finish. And in fact, I did it by hand just for fun. And I'm like, I'm get out of this. And then I went to Symbol Lab, not for number 1, but for the rest of the test. So I was not careful on the rest of the test to make sure all the numbers are nice, because I figure if you're using technology, I don't care if the numbers are nice, and hopefully you don't either. Are you good with that? So there are a lot of questions where you do use technology, but you have to know the steps to do. Does that make sense? You have to show your work, and showing your work does not mean, so like, for example, if I let you use technology, then you don't have to show your work in RREFing, but you have to have the words RREF down, or the letters. Sound fair?
Yeah.
Okay, so that's what I want. I want what you did, not all the details of arithmetic that the computer did. Do you see the difference? Any questions on that? Okay, let me go through more of the test, because we have some more time. So that was number 1. And let me know if you have any questions about any of these problems. I'll be happy to, either answer or tell you I'm not going to answer, one or the other. Okay, so let me read you page number 2. For the rest of exam, you may use a computer to perform any matrix operations or manipulate matrix, but show what you are putting into the computer and what the computer gives. Okay, does that sound fair?
Yeah.
So that's the instructions for the rest of the exam. Okay, problem number 2. Problem number 2, you're used to me doing this. Most of you have had me as an instructor, not almost all of you, I think. And what do I often ask? Almost every test.
True or false?
Yep. So number 2 is, but now we're more advanced. So you're going to hate the last part of the instructions, but let me read it anyway. So answer the following questions, true or false, and prove that your answer is correct. So I didn't used to use the word prove, but guess what? We're in linear algebra now. So yeah, you need to prove. Sound fair? Not too unexpected. And there's a bunch of those because they're important. So just a note, to prove something's false, what's the easiest way usually to do that?
Find one example in which it's false.
Exactly. Find one example which is false and you've proven it's false. If you find one example that it's true and you say therefore true, what am I going to do?
Not
You're
give
gonna
us
find-
points.
Yeah,
I'll give you a few points.
you're gonna find
but
one example.
You're not going to
in
get a
which
lot of
false.
points. Yeah. So if it's true, it's actually a lot harder. Does that make sense? Okay. And I will tell you, I mean, I don't have to tell you, but I'm going to tell you anyway. There are multiple parts of this one, and it's not all true and it's not all false. Got it?
Oh God, that sounds menacing.
Yeah. So there's trues and falses. So in other words, don't just assume they're all true or all false, because that's not going to happen. And I also am not leaving a lot of space to work it out. And the reason is, and maybe I'm wrong, but I don't think you're going to print it out anyway, are you? Maybe you will.
I'm definitely not.
I don't even have a printer at home. I've never printed it out. So that's why I didn't bother with space, because I didn't think it needed. So, just because I didn't leave much space does not mean it won't take space. Sound fair? So again, I'm in new grounds here. So there's an A, B, C, D, and E on this one. Okay, the next question is an application question. I'm not going to tell you what it is, but we've had some applications. The next question, and I'll even say the next couple questions, have to do with kind of the most and deepest section we've had, which is that.
4.10.
Yeah. And what are the main things we did in 4.10? Big things.
Subspace.
Subspace. What else?
Linear independence.
What else?
Linear combination.
What else?
Bases.
Yep. There's another word. The other biggie. Starts with an S?
Span.
Yeah. Caesar's got it. Yeah. So span. So, know how to show something spans, linear independent, what is the basis, what's the dimension, all that kind of stuff. Or to show that it doesn't span or something like that. Any questions on that? Okay. And I'm giving you, I'll give you vectors, but you have to know what to do with the vectors. And you're going to make matrices, and then you can use a computer to do what you need to do to RREF. Got it? Does that sound fair? Okay, next one. So that's the next couple, by the way. Actually, the next three. So 4, 5, and 6. Because that section 10, that's the 4.10 is the big section of this class. Okay.
Is there a section that even comes close?
No.
Okay.
No. I mean, if you didn't understand the first section and you don't know what a matrix is, that'd be bad, but no one has trouble with that section. Do you agree?
Yeah.
Yeah. So that, if you don't know what a matrix is, you can't do anything in this class, right? Or very little. But in terms of tough stuff that was intense, that section covered half the class. Okay. Then the next two problems come from the newest stuff. What's the newest stuff? And not today. Or not what we lectured on today, because that's not on the test. So what is the newer stuff?
Projections.
Yeah.
Orthogonal matrices.
What else?
Orthogonal bases.
So orthogonality is a general concept.
Orthogonality. What else?
Orthonormality.
Orthonormality. What else?
least squares solutions.
Squares. Okay, good. So right now I have two problems. I have a feeling I'm going to get rid of one of them just to make it a little shorter. What do you guys think? Now that you've heard how long the test is. That's the end of the test, except for the very last question, which you all know what it is. Or most of you know. What's the very last question?
It's asking for your honor,
Feedback,
basically.
right?
Or
No,
no, it
actually,
is feedback.
An honor one, but huh?
Feedback, right?
Yeah, I always give that one. And you, by the way, you'd be a fool not to do that one because that's free points. Take free points. That's the X credit problem. I give that on every class I ever teach. So that's about it. I'm going to stop the recording because that's kind of what the test is. I don't know if that helped or not, but I read through the test is what I did.